Okay, last time we have started the context of a process. In that, we have seen the system level context consists of the following components, that is, the several process share common regions, that is, a region considered part of context of each process because each process manipulates the regions independently. The part of memory management task is to indicate which part of virtual address space of a process are not memory resident, that is, a data stored or contents of a process are stored in a memory which is in continuous or non-continuous format, so that kernel stack contains the stack frames of kernel procedures as a process executes in kernel mode. Although all processes execute the identical kernel code, they have a private copy of kernel stack which specifies their particular invocation of kernel functions. The dynamic part of system level context of a process consists of a set of layers visualized as in last in first out manner because the processes execute in kernel code, identical kernel code, and that kernel code, that is kernel stack, contains the stack frame of kernel procedures as the process execute in kernel mode, that is last in first out manner or first in last out manner. So each system level context layer contains the necessary information which cover the previous layer, including the register context of previous level. So kernel pushes the context layer. Kernel pushes the context layer when an interrupt occurs, when a process makes a system call, or when a process does a context switch. The pops It pops the context layer when kernel returns from the handling interrupt, when a process returns to user mode after the kernel completes execution of system call, or when a process does a context switch. So context switch thus essential or entails a push and pop of system level context layer such that the kernel pushes the context layer of old process and pops up context layer of new process. So process table entry stores the necessary information to recover the current context layer. See in this figure, that is a component of the context of a process. See the figure carefully. See in this see in this figure, the left side portion is a static portion of context, which consists of two parts: user level context, in that process take text, data, stack, and a shared data. Then another part is a static part of system level context, that is process table entry, user area, per process region table. And the right side part is a dynamic a portion of context. There are number of layers from layer 0, layer 1, layer 2, layer 3, and so on, which is dynamically. So each layer consists of the kernel stack, where saved registered context at particular layers. Kernel context layer 0 is used for user level, and from layer 1 to number of layers, it is used by kernel level. So this figure shows the components that form context of a process. The left side of figure shows the static portion of the context. It consists of user layer context containing process text, data, stack, shared memory, and a static part of the system level context which contains process table entry, user area, then private region entries. Then right side of this figure shows the dynamic portion of the context, which consists of several stack frames where each frame contains saved register context of the previous layer. See here a layer 3 context a stack for layer 3, which shows the information saved register context for layer 2. See in layer 2, there is a saved register context for layer 1. That is, the frame contains a saved register context previous layer and kernel stack as kernel execute in that layer. System context layer 0 is a dummy layer which represents user layer level context. Growth of stack, here is the user address space. Here is user address space or user level context, that is growth of stack, user in that user address space, and kernel stack is null. So there is an arrow from the static portion to dynamic portion, that is top level of dynamic portion of the context level, which represents a logical information stored in that process table entry, which shows the logical information stored in process table entry to enable the kernel to recover current context layer of the process. So a process runs within a context. A process runs within its context, or more precisely within its current context layer. The number of context layers is bounded by number of interrupt levels of machine support. For example, if machine supports different interrupt levels, if machine supports different interrupt levels for software interrupts, terminals, disk, or other peripherals, and the clock, it supports 5 interrupt levels, and hence the process can contain at most 7 context layers: one for interrupt level, one for system call, and one for user level. The 7 layers are sufficient to hold context layers even if interrupt occur in the worst possible sequence, because an interrupt of a given level is blocked while the kernel handles interrupt of that level or higher. Although the kernel always executes in the context of some process, the logical function that it executes does not necessarily pertain to the process. Then, saving the context of a process, the kernel saves context of a process whenever it pushes a new system context layer. In particular, this happens when a system receives an interrupt, when a process executes a system call, or when a kernel does a context switch, that is interrupt and exceptions, system call interface, context switch, copying data between system and user address space. So interrupts and exceptions. The system is responsible for handling interrupts, whether they result from hardware, that is as from the clock or from peripheral devices, or from programmed interrupts such as execution of instructions designed to cause software interrupts, or from exceptions such as page faults. So system is responsible for handling interrupts whether the result from hardware or software or from such from exceptions such as page faults. If the system is executing at lower processor if the system is executing at lower process execution level than the level of interrupt, it accepts the interrupts before decoding the next instruction and raises the processor execution level so that no other interrupts of that level can happen while it handles the current interrupts, preserving integrity of kernel data structures. If the CPU is executing at lower process execution level than the level of interrupt, it accepts the interrupt before decoding next instruction. It accepts the interrupt before decoding next instruction and raises the process execution level so that no other interrupts of that level can happen while it handles the current interrupts and preserve the integrity of kernel data structure so that kernel handles interrupts with the following sequence of operations such as it saves current register context of executing process and creates into new layer. It determines the source and cause of interrupts, identifying types of interrupts and unit number of interrupts if it is applicable. So it determines what is the source of interrupt, what is the reason of that interrupt, and then type of interrupt, number of units or unit number of that interrupts. So when system receives an interrupt, it gets a number from the machine that it uses as the offset into table, commonly called an interrupt vector. The component of interrupt vary from machine to machine, but they usually contain the address of the interrupt handler for the corresponding interrupt source and the way of finding parameters for interrupt handler. So kernel invokes the interrupt handler. A kernel stack for the new context layer is logically different from the kernel stack of the previous context layer. So what is where is the top of that stack? That is a toss, the kernel toss of the new context layer, which is logically different from the kernel toss of previous context layer. And some implementations use kernel stack of executing process to store interrupt handler stack frames, and other implementations use a global interrupt stack to store the frames for interrupt handler that are guaranteed to return without switching context. So the interrupt handler completes its work and returns. The kernel executes machine specific sequence of instructions. Kernel executes a machine specific sequence of instructions that stores uh, the register context and kernel stack of previous context layer as they existed at the time of interrupt, and then resumes execution of the restored context layer. The behavior of process may be affected by interrupt handler. Since interrupt handler may have alerted global kernel data structures and awakened sleeping processes, that is that processes which are in a sleep mode. So see, this is the algorithm for interrupt handler. Algorithm interrupt hand, that is int hand, input is none, output is none. So the process is save the current context layer, determine the interrupt source, find the interrupt vector, call interrupt handler, and restore the previous context layer. So this algorithm summarizes how kernel handles interrupts. Some machines do part of the sequence of operations in hardware or microcode to get better performance than if all operations were done by the software. But there are trade-offs based on how much context layer must be saved and the speed of the hardware instructions doing the save. So this figure shows the example of interrupt where the process issues the system call and receives a disk interrupts while executing the system call. See in this figure, there are different types of interrupts such as clock interrupt, disk interrupt, then system call interrupt executing. So while executing in user mode, there are different types of interrupts. So disk interrupt handler, the system receives the disk interrupt handlers, the system receives the clock interrupt and execute the clock interrupt handler. Every time the system receives an interrupt, it creates a new context layer. Suppose interrupt due to system call, it creates a new system call, it creates a new context layer. For suppose here interrupt due to system call, it creates a new context layer, layer 1. So for executing that system call, After some time there is interrupt of disk. So there is another context layer to execution of for disk, and so on. So every time the system receives an interrupt, it creates new context layer and saves register context of the previous layer. Then first we will see the system call interface. The system call interface to the kernel has been described in previous chapter, that is in fourth chapter we have seen the different types of system calls. So usual calling sequence, not a change mode of a process from user mode to the kernel mode, or from kernel mode to the user mode. That is, C compiler uses a previous predefined library functions, that is named system calls. Such system calls such as PID, that is process ID, or PWD, process print working directory, or ls. These are different commands we have seen, date, who I am. So these different commands as known as system calls. It is also known as a system calls. So resolving system call reference in user program to what would otherwise be undefined names. Then library functions typically involve an instruction that changes the process execution mode to kernel mode and causes the kernel to start executing code for system call. So the ensuing discussion refers instruction as a operating system trap. So the library routines execute in user mode, but the system call interface, that is in short a special case of interrupt handler. The library functions pass kernel to unique number per system call in the machine dependent way, either as a parameter to the operating system trap in a particular register or the stack and the kernel, and thus determining the specific system call the user is invoking. This is the algorithm for a system call. See this algorithm carefully. See, this is algorithm syscall, that is system call. Algorithm for invocation of system call: input system call number, output result of system call. The process Find the entry in system call table corresponding to the system call number. Determine number of parameters to that system call. Copy parameters from user address space to user area. Save current context for operative, then return. Invoke system code in kernel. If error during the execution of system call, then set register 0 in user space register context to error number. Return on carry bit in process state register in or in user saved register context. If there is error occur, if there is no error occur, in set register 0, 1 in used register user saved register context to return values from system call. This is the algorithm for system call. So in handling the operating system trap, the kernel looks up the system call. Kernel looks the system call number in table to find the address of the appropriate kernel routine, that is the entry point for system call, and to find number of parameters to the system call expects. The kernel calculates, that is user address of the first parameter to the system call by adding or subtracting depending on the direction of the stack growth. If stack growth is going upwards, that is adding. If top of the stack going towards downwards, there is subtraction. So kernel calculates user address of the first parameter to the system call by adding or subtracting an offset to the user stack pointer corresponding to the number of parameters to the system call. And finally, it copies the user parameters to the user area and calls to the appropriate system call routines. So after execution of the code or executing the code for the system call, the kernel determines whether there was error. If there was error, it adjusts register locations in the saved user register context, typically by setting the carry bit for the process state register and copying the error number into the register 0 location. If there were no errors in the execution of the system call, the kernel clears the carryout bit in the process state register and copies the appropriate return values from the system call into the location registers 0 and 1 in the saved user register context. When kernel returns from the operating system trap to the user mode, it returns to the library functions after the trap. The library interrupts return values from the kernel and returns to the value to the user program. See this figure carefully. This figure for process state a transition diagram. See this figure carefully once again. referring to this process state transition diagram, we see that kernel permits context switch for under four circumstances. That is, when a process puts off its sleep mode, that is from the second state, that is kernel running mode. See in this figure, that is first circumstances, the processes which are go to the sleep mode by itself, that is go to the fourth number step. When it returns from the system call to the user mode, but not the most eligible process to the run, that is it goes to the from user mode, that is from step first from user mode to the kernel mode, but that processes are not ready to execute, so go to the preemption state. Or when it returns the user mode after, or either either it returns to the user mode after it completes handling an interrupt but not eligible processes to run. These are the three ways. First, the processes which are goes to the sleep mode by itself. This is first step. Second, the processes enters due to some interrupts from user mode to the kernel mode. So again, it returns to the user mode. This is second step. And third step, the process enters from user mode to kernel mode, but they are not ready to execute. So though they are not ready to execute and they have entered in kernel mode, they go to the preemption state, that is step number 7. This is third. And fourth step, they goes to the Zumba state for execution. So kernel ensures integrity and consistency of internal data structures by prohibiting arbitrary context switches. So it makes sure that state of its data structure, it consistent before it does the context switch. That is, that all appropriate updates are done, that queues are properly linked, that appropriate locks are set to prevent intrusion by other processes, that no data structure are left unnecessarily locked, and so on. For example, if kernel allocates a buffer, reads a block in a file and goes to the sleep waiting for IO transmission from the disk to complete, it keeps the buffer locked so that no other processes can tamper with the buffer. But if a process executes the link system call, the kernel releases the lock of the first inode before locking the second inode to avoid deadlocks. So kernel must do the context switch and the conclusion of exit system call because there is nothing else for it to do. Similarly, kernel allows a context switch when a process enters a sleep state, since a considerable amount of time may elapse until a process wakes up and other processes can meanwhile execute. The kernel allows a context switch when a process is not the most eligible to run to permit fairer process scheduling. That is, a process completes a system call or returns from interrupt, and there is another process with higher priority waiting waiting to run. It would be unfair to keep the high priority process waiting. The procedure for context switch is similar to the procedure for handling interrupts and system calls, except that the kernel restores the context layer of a different process instead of the previous context layer of same process. The reason for context switch are irrelevant. Similarly, the choice of which process to schedule next is policy decision that does not affect the mechanism of the context switch. So the code that implements the context switch on Unix system is usually the most difficult to understand in the operating system because the function calls give the appearance of not returning on some occasions and materializing from nowhere on others. This is because kernel in many implementations save the process context at one time in the code but proceeds to execute the context switch and scheduling algorithms in the context of the old process. When it later restores the context of the process, it resumes the execution according to previously saved context. To differentiate between the case where kernel resumes the context of new process and the case where it continues to the execute in the old context after having saved it, the return values of critical functions may vary, or the program counter where the kernel executes may be set artificially. Then next part, a copying data between system and user address space. A process executes in kernel mode or in user mode with no overlap modes. However, many system calls examined in the moving data between kernel and user space, such as when copying system call parameters from user to kernel space, or when copying data from IO buffers in the read system call. Many machines allow the kernel to reference addresses in the user space directly. The kernel must ascertain a kernel must ascertain that address being read or return is accessible as it had been executing in user mode. Otherwise, it would override the ordinary protection mechanism and inadvertently read or write addresses outside the user address space. Therefore, copying data between kernel space and user space is an expensive proportion requiring more than one instruction. Then moving data from user to system space on a VAX. See in this table, a VAX code for moving one character from user address space to kernel address space. So the proper instruction, see in this table, this is proper instruction, checks 1 byte address, checks 1 byte address at argument pointer register 4 plus 0, register plus 4, that could be read in user mode 3. If it is not, the kernel branches the address erect and stores 1 in register 0 and returns character move failed. Otherwise, the kernel one from byte moves 1 byte from the given user address to register 0 and then returns that the value to the caller. The procedure is expensive, requiring 5 instructions with the function call funcbyte to move 1 character. And this is the end of your chapter.